Welcome back to this channel, and we are on lecture 4 of the special topics in physics, and we are to deal with Coulomb's law under electrostatics. We all know that charges are traced to a basic particle in nature called atom, and we have electrons that are negative surrounding a dense and a positive nucleus where protons and neutrons reside. Since neutron has zero charge, we will forget it for a while and focus on protons and electrons, which directly participate in electrostatic reactions. You also need to remember the three properties of charges. First, the charges could either be positive or negative. Second, the smallest of a charge is called an elementary charge, which has a value of 1.6 times 10 raised to 9 coulomb. And coulomb is the unit of charge. And 1 coulomb is equivalent to 6.24 times 10 raised to 18 electrons. It means that you need 6.24 times 10 raised to 8 electrons to be taken away or added to an object for you to charge it with a positive or a negative one. If we are also to go back with our previous lecture on universal law of gravitation, we do remember that F, or the gravitational force, is equal to G times M1 times M2 over R squared. That is for any object separated from another object at a distance r. Let us label it as object 1, and this is object 2. So what do we know about it? So M is the mass in kilograms, and G is the constant 6.67 times 10 raised to negative 11 Newton meter squared per kilogram squared. We also have R, which is the distance between, in this case, we have 1 and 2, the distance between the center of the two objects. So what can we say about the attractive force existing between these two objects? So the force is always an attractive force, which means that the force that the object 1 experiences is towards object 2, and object 2 experiences a force from object 1 that is directed to this direction. Also, the mass is always positive, so there's no negative mass or negative value for the mass. If you compare it with Coulomb's law, you have the symbol Fe. So I will use the electrostatic force instead of Coulomb's force, since we still have centripetal force for uniform circular motion. The electrostatic force is equal to a constant times the product of the two charges and the square of the distance, where Q is the charge in Coulomb, and we have the constant K, which came from the equation 1 over 4 pi squared 4 pi permittivity constant in free space, which is equivalent to 9 times 10 raised to 9 Newton meter squared per coulomb squared. And R is the distance between the two charges. Now, what can you say about the force existing between these two charges? So the force can either be an attractive force or a repulsive force, as we know in the law of charges. And the charge can either be positive or negative. So let's compare the magnitude of the forces of gravitation and electrostatic forces by considering again the mass of object 1 and the mass of object 2 at a distance. And Let us say that the mass of the two objects are 1 kilogram each, and for a charge, we have a positive 1 charge. Using our first equation, G is equal to Fg is equal to G times 1 kilogram times 1 kilogram over the square of the distance, assuming that this is 1 meter, and we get an answer of 6.67 times 10 raised to negative 11 newtons. How about in Coulomb's law? So Fe is equal to K, that's a constant, that's a value of 9.0 times 10 raised to 9 Newton meter squared per Coulomb squared, multiplied by positive charge 1 and another positive 1 charge over the square of the distance, and we get 9.0 times 10 raised to negative 9 newtons. Looking at this value, we can say that the electrostatic force is a lot stronger in terms of magnitude, and that is about 10 raised to 20 that of the force of gravity. Let's have a more uh, concrete example using the attractive force between an electron and a proton in a hydrogen. So what information do we need to get first? So the mass of an electron is equal to 9.11 times 10 raised to negative 31 kilograms. And the mass of the proton is 1.67 times 10 raised to negative 27 kilograms. And then one charge, Q, is equivalent to 1.6 times 10 raised to negative 19 Coulomb. And let's draw it. We have here a positive charge proton that is interacting with an electron, and their distance in a hydrogen atom is 5 times 10 raised to negative 11 meters. Let's use the equation now. So you have Fg is equal to the gravitational constant me times the mass of the proton over the square of the distance. You have 6.67 times 10 raised to negative 11 Newton meter squared per kilogram squared times the mass of electron 9.11 times 10 raised to negative 31 kilograms multiplied by the mass of proton 1.67 times 10 raised to negative 27 kilograms over the distance of 5, this is the distance, 5 times 10 raised to negative 11 meter squared. And we have an answer of 4 times 10 raised to negative 47 newtons. This is the gravitational force that exists between an electron and a proton. What about if we compute for the electrostatic force between them? So you have the formula K is equal to Q1 times Q2 over R squared. So mass is not considered in this equation anymore. So we have the value of K, it's 9.0 times 10 raised to 9 Newton meter squared per Coulomb squared times the value of the charges. We have 1.6. Since one charge is also equivalent to 1.6 times 10 raised to negative 19, whether it's positive or negative, we just need to square it. 1.6 times 10 raised to negative 19 Coulomb squared over 5.0 times 10 raised to negative 11 meters squared. and we get an answer of 9 times 10 raised to negative 8 newtons. So the value of 9 times 10 raised to negative 8 newtons is about 10 raised to 40 times of that of gravity. So really, electrostatic force is a stronger type of force compared to gravitational force. But we don't take away the force that gravity applies to heavenly bodies like the moon, stars, and even on the earth. So we can now state Coulomb's law using our equation as the attractive or repulsive force between two charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. So in equation form, that's electrostatic force is equivalent to K and is directly proportional to the product of the two charges but is inversely proportional to the distance between them. So please remember that electrostatic force is a mutual force and it always comes in pairs of equal magnitude and acting in opposite direction along the line connecting the two charges. If we go back with our law of charges, so a positive charge interacting with a positive charge will cause the two charges to move away from each other. If this is charge 1 and charge 2, so charge 1 experiences a force, repulsive force from Q2. That is 1, 2. Force 1, 2, that's directed to the left, while this one experiences a repulsive force to the right because of Q1. That is F denoted by 2, which is the charge, and the charge that causes it to move this way. If we have two, a positive and a negative charge, so it will cause an attractive force for each, so that will be an attractive force. So we denote a positive sign if there's a repulsive force existing between the two charges and a negative sign for attractive forces. So the same happens for two negative charges. They will just repel from each other along the line of connecting the two charges, and that will be a positive sign in our convention. Let us try it using 4 examples. So we have here the first one. A charge of 2.5 times 10 raised to negative 18 Coulomb is placed 3.0 times 10 raised to negative 6 meters away from another charge of negative 4.0 times 10 raised to negative 9 Coulomb. What is the force of attraction between them? So let's say we have here the first charge, Q1, and then that is placed about 3.0 times 10 raised to 6 negative 6 meters away from the second charge, which is a negative charge. So let's write the given. So our given are Q1 2.5 times 10 raised to negative 18 Coulomb. Q2 is negative 4.0 times 10 raised to 9 Coulomb. 19, that's raised to negative 19. And we have the distance 3.0 times 10 raised to negative 6 meters. And we are to look for the electrostatic force between the two charges. The equation simply is Fe is equal to K Q1 times Q2 over R squared. Let us substitute the values to our equation. We have Fe is equal to 9.0 times 10 raised to 9 Newton meter squared per Coulomb squared times 2.5 times 10 raised to negative 18 Coulomb times the absolute value of 4 times 10 times 10 raised to negative 19 Coulomb. So you see, we use the absolute value of the charges since it will affect our decision on or determination of where the force is going to. So later we'll find out what is the direction of the force. Divided by the distance, that's 3.0 times 10 raised to negative 6 meters, and that is squared. So we write this one, 9.0 times 10 raised to 9, so that we can see the canceling out of the units. So 2.5 times negative 4, it's 10. We have 10 times 10 raised to negative 37 Coulomb squared over the square of the distance, that is 9 times 10 raised to negative 12 meters squared. So we can cancel out the units, meters, and Coulomb, and proceed with our calculation. So 10 over 9, so I did not change the 10 into value 0 to 9 yet, so I'll compute it first. 10 over 9 has a value of 1.11 times 10 is 1.11 times 10 raised to negative 25. And we have an answer of 1.0 times 10 raised to negative 15. And I write it again, 1.0 times 10 raised to negative 15 newtons. So we did not get any negative value, even if there is a negative charge interacting with Q1. So how do we know if we will consider it as positive or negative in this situation? If we are to look at this positive charge and we say there's an attractive force, so by convention, since it's an attractive force, it's a negative value of the force. And also, using our vectors, so anything that is going to the right will give us a positive value. So which will we follow? We'll follow the vector, direction of the vector that is positive. So if the force that Q1 experience from due to Q2 will have a positive sign of 1.0 times 10 raised to negative 15. But if you gonna take a look at or your perspective is in Q2, so that will be a negative sign since the charge, this negative charge, will move to the left. So for second example, how far apart must two electrons be if the force between them is 1.0 times 10 raised to negative 12 newtons? So we have two electrons denoted by the two negative charges here, and the distance between them is missing, but we have the electrostatic force which is 1.0 times 10 raised to negative 12 Newton, as also given here. So what is the value of the electrons? So since the simplest and the smallest unit of elementary charge is 1.6 times 10 raised to negative 19, 19 Coulomb, we'll use it as the value of the two electrons. So we now have our given, and we are required to look for the value of R. And our equation comes from our basic equation Fe is equal to K Q1 Q2 over R2. So we need to derive the equation for R2. So that's cross multiplication Fe R squared is equal to K Q1 Q2. Then divide both sides by Fe. And we get R squared which is equal to K Q1 Q2 over Fe. We can still simplify it since we have two electrons. We have the same charges. So we can simplify Q1 and Q2 into simply Q2, so that when we eliminate the square of R, we'll have this equation. Let's write it. R squared is equal to K. This is Q squared already, since we have the same charges interacting. Then we have Fe. So we need to eliminate the square of R. So this will be R, and then eliminate this one. We get Q is equal to K times K is equal to Q times the square root of K over Fe. And we are now ready for our solution. So R is equal to Q. So value of Q, it's 1.6 times 10 raised to negative 19 Coulomb multiplied by the square root of K. It's 9.0 times 10 raised to 9 Newton meter squared Coulomb squared over the force 1.0 times 10 raised to negative 12 newtons, and we get 1.6 times 10 raised to negative 19 Coulomb and the value of this division we have inside the square root sign. It's 9 times 10 raised to 21. Multiplying the square root of 9 times 10 raised to 21 with the value of the charge, we get an answer of 1.52 times 10 raised to negative 8 meters. So that is the distance between the two charges. Let's have number 3. Okay, for number 3, we are to deal with 3 charges that are aligned to each other. So we will follow an extension of Coulomb's law, which is the law of superimposition. In this law, it states that all linear forces, that for all linear forces, the total force is a vector sum of the individual forces. So the forces that affect Q1 will not be affected if we add another charge in between or on any side or any part of the system. So let's label our figure. So this positive charge is Q1, then this is Q2 and Q3. And let us say that the distance between Q1 and 2 is 2 centimeters. And for the two negative charges, let us say there's a 3 centimeter distance. Q1 has a positive 3 microcoulomb charge. Q2 is negative 8 microcoulomb, and you have another negative 8 microcoulomb. So the question is, calculate the force or the net force acting on Q2 due to Q1 and 3. So let us see. Since this is opposite charges, the Q2 experience an attractive force that is going to the left. That is the force experienced by 2 due to 1. How about this one? So this is a repulsive force. So if this is Q2, it also experiences a force that is directed to the left. That is 2 force experienced by charge 2 due to 3. So these are the two forces that we need to compute and get the net force. So we have F21 is equal to K Q1 Q2 over R2. So the value of K is 9.0 times 10 raised to 9 Newton meter squared per Coulomb squared times the value of Q1. So this is Q1, 3 times 10. So a micro Coulomb or micro is equivalent to the power of 10 raised to negative 6 times the charge of Q2 negative 8 times 10 raised to negative 6 Coulomb over the distance of 2 centimeters. Let's convert it into meters. That is 0.02 meters squared. So we have this one. So I'm rewriting it so that it will be step by step. So 3 times negative 8, that's 24 times 10. So that's negative 6 plus negative 6. It's negative 12 Coulomb squared over the square of 0.02, that is 4 times 10 raised to negative 4 meters squared. So we cancel out all similar units. So we get 9.0 times 10 raised to 9 newtons multiplied by the quotient of these two values, which is 6 times 10 raised to negative 8, and we get an answer of 54 times 10 raised to 1 newtons. Let's put it in standard notation. That will just be 540 newtons. This is the force exerted by charge 1 to charge 2, which is an attractive force, and that is a force going to the left. How about the force of Q3 on Q2? Let's write it on top. So that is the force experienced by charge 2 due to 3. So get an equation of K, Q2 times Q3 over R. So we write the value of the constant and then multiply it by the values of the charges, negative 8 times 10 raised to negative 6 Coulomb multiplied by another negative 8 times 10 raised to negative 6 Coulomb over the distance between them. So the distance is 3 centimeters. So that's 0.03 meters. And we get 9.0 times 10 raised to 9 per Coulomb squared. Negative 8 times negative 8. So we get an absolute value. We have 64 times 10 raised to negative 12 Coulomb squared over 9 times 10 raised to negative 4 meters. We cancel this out again, and we get 9.0 times 10 raised to 9. And this value is 7.11 times 10 raised to negative 8. And we just need to multiply it. Okay. So my answer here is 64 times 10 raised to 1 newtons. In standard form, that is 640 newtons. So this is an attractive force. This is a repulsive force. Okay, but if we want to compute for the net force, we consider the direction of the force and not the charge of the object, and even the convention that we use for attractive or repulsive force. So if we compute the net force, F net is equal to F21 plus F23. So since this one is going to the left, so we get a value of 540 newtons plus 640. So it makes Q2 also move to the left by its repulsive force. So we have negative 640 newtons. So the total force is 1,180 newtons to the left. Or if you put a negative sign, that is understood. But I will remove it now. 1,180 newtons towards left or towards Q1. Remember this because we'll put this in our total net force or the net force of the system. For the sake of practice, let us compute for the net force acting on Q1 in our example. So we have here a positive sign again, and then earlier we had the negative charge and a negative charge. So we are concerned with how much force is acting on Q1. We're done with Q2 in our example. So we are to practice computing for the net force in Q1. Imagining that these are interacting already. So Q2 puts an attractive force to Q1, and that is directed to the right. This is force 1 due to 2. How about this one? So how does it affect Q1? So since this is also a negative charge, so it causes an attractive force. So that is also directed to the left. Since we already computed for the value of 2, 1 earlier, that will be also equal to the value of 1, 2, but we will change the direction. So 2, 1, value of 2, 1 is 540. So this is also 540 newtons. So our only concern here is to compute for the force that charge 1 experienced due to charge 3. And that is K Q1 Q3 over R squared. So you have 9.0 times 10 raised to 9 Newton meter squared Coulomb squared times Q1. What's the value of Q1 again? That is 3 microcoulomb. So you have 3 times 10 raised to negative 6 coulomb times negative 8 times 10 raised to negative 6 coulomb. Again, we get absolute value over the distance. So the distance is not 2 centimeters, it's 3 centimeters. So 0. No, it's since we have 0.2 meters or 2 centimeters here, so the total distance is 5 centimeters. That is 0.05. So write this again. So 3 times negative 8, it's 24 times 10 raised to negative 12 Coulomb squared, and we have 2.5 times 10 raised to negative 3 meter squared. and we get a value of 9.0 times 10 raised to 9 times 9.6, 9.6 times 10 raised to 9. This is the quotient of these two values, and we get an answer of 86.4 newtons. So we say that this is positive, this one, since it's going to the right. So what is the net force in this that Q1 experiences? So you have a net force is equal to F2, F12 plus F13, get 540. That's F1, F net is equal to F12 plus F13. So we have a value of 540 newtons plus 86.4 newtons. We get 626.4 newtons. Okay. So what if we also want to look for the force that Q3 experiences due to Q1 and Q2? So that is quite easier now, since for Q3, we already solved it earlier, because the force that it experiences from Q1 is also the same force that we have computed for the force experienced by Q1 due to 3, which is 86.4. Since Q1 is positive, so it is Q3 is attracted to the positive charge, and this will have a negative sign. And then F32 is also equivalent to the computed value of F23, which is 640 newtons. So that's a negative charge. So Q2 is a negative charge, so it causes a repulsive force that is going to the right, so it remains as 640 newtons positive. And we get the net force, negative 86.4 plus 640, we have 554 newtons. Now, computing the net force of the system, what I mean is all the forces from 1 up to Q3. So we write F1 plus F2 plus F3. So F1 is here. So this is the net force of Q1, or that Q1 experiences, 626.4 newtons, that is positive, plus F2. So earlier we computed it. It is 1,180 directed to the left. So that has a value of 1,180 newtons, plus F3, this one, which has a net force of positive, which means it's going to the right direction, of 554 newtons. And adding all of this, we get 0 as our net force. For last example, what if we have 3 charges that are positioned like this? So we have Q1, so let us assign this as Q1, this is Q2, and we have a negative charge Q3. So we do not have any value for this distance, but we know Pythagorean theorem, that is 3, 4. We have an adjacent side of 3, and an opposite side of 4 meters. That's 3, 4, 5 theorem. So this is 5 meters without any computation. Let us examine first what is the direction of the force that we are about to compute. So we are concerned with the net force acting on Q1 due to Q2 and 3. So since this is these are both positive charges. So we are sure that this charge will move away from Q2 in this direction. So this is the force experienced by Q1 due to Q2. Now, how about this one? So since they are opposite charges, so there is an attractive force existing between them. So this one is going to that direction. And we call it the force experienced by charge 1 due to charge 3. So we are to compute these two forces. Okay, so let's put our values now. So for Q1, so we have a positive 2.0 microcoulomb. Q2 has a positive 7.0 microcoulomb. And we have a negative 7.0 microcoulomb for Q3. We have here the distance 6 meters between the positive and negative charge Q2 and Q3. And then we already got the value of R for Q1 and 2. So we can now proceed with our calculation. So for F1 and 2, for F1, 2, that is K is equal to Q1, Q2, that's F12 is equal to K times Q1 times Q2 over R squared. Let's substitute the values. 9.0 times 10 raised to 9 multiplied by 2.0 times 10 raised to negative 6. Again, microcoulomb is equivalent to the power of 10 raised to negative 6 times 7.0 times 10 raised to negative 6 coulomb over a distance between them that's 5 meters squared, and you get a value of 14 just on top. 14 times 10 raised to negative 12 over 2.5 times 10 raised to 1. Okay, solving for this, we get 5.0 times 10 raised to negative 3 newtons. Let's now have F13. You have 9.0 times 10 raised to 9 Newton meter squared per coulomb squared times, so we have Q1 and 3, that's 2.0 times 10 raised to negative 6 coulomb times negative 7.0 times 10 raised to negative 6 coulomb, all over the distance between them, which is just the same with the distance of Q1 and 2, which is 5 meters. We get this answer of so that's 2 times 7, so it's just the same. 14 times 10 raised to negative 12 over 2.5 times 10 raised to 1. And we get an answer of 5 times 10 raised to negative 3. As you see, they're just the same as how we computed it. Although the value of the charges Q2 and Q3 are different, you can still have the same answer for both quantities. So we're through with drawing the forces. So it's our first step. Our second step is to compute for the values of F12 and F13. We are now to add the vectors. Since it is at an angle, we need to look for the x and y components of the two forces. So we have here an angle, and we have the values of the sides of the right triangle. So it's easy for us to compute using trigonometric functions. So let's begin with the components of f(1,2) x. It is 1, 2 cosine theta. Remember that in trigonometry, cosine theta is equivalent to the adjacent side over the hypotenuse. So we have here this is the adjacent side, this is the opposite side, and this is the hypotenuse. So adjacent over the hypotenuse. So what is the value of it? So that's 5 times 10 raised to negative 3. 3 over times 3 over 5. And we get an answer of 3 times 10 raised to negative 3 newtons. For the y component, we have f(1,2) sine theta, and sine theta is equivalent to opposite side over hypotenuse. So that's 5. Actually, that's 4. 5 times 10 raised to negative 3. That's 4 over 5. This is the value of the opposite side and the hypotenuse. We get an answer of 4 times 10 raised to negative 3 newtons. What about the x and y component of this f(1,3)? So f(1,3) x is equal to f cosine theta. So we use the same numbers for the opposite, adjacent, and hypotenuse. So you have 5 times 10 raised to negative 3 times 3 over 5. We get 3 times 10 raised to negative 3 newtons. You see, we have positive signs for the x and y components of 1,3. 1,2. Why? So if you look at it, this one is the direction of the force 1,2. If you get the x and y component, so this is the Cartesian plane directed to the right, so that will have a positive sign. This one, the y component is going up, that will also have a positive sign. So we are correct with this one in saying that this is 3 times 10 raised to negative 3, and this is 4 times 10 raised to negative 3. For f(1,3), this is the direction of the force, the attractive force that affects Q1. So if you get the component, so this is the x component of this, that is f(1,3)x, so that remains positive. But the y component of f(1,3) is going downward in the Cartesian plane from the origin. So let us see what will be our answer now. So f(1,3) y is equal to a negative sign already, negative f sine theta. And using opposite in the hypotenuse, so we now compute 5 times 10 raised to negative 3. 4 over 5 is equal to negative 4 times 10 raised to negative 3 newtons. So we now have the values of the x and y component. It's now time for us to add the components, or the add like components of vectors f(1,2) and f(1,3). So for fx, the component of the x component of the force, that is F12x plus F13x. So they have the same value, 3 times 10 raised to negative 3 newtons plus 3 times 10 raised to negative 3 newtons. We get 6 times 10 raised to negative 3 newtons for the x direction. For y, you get F12y plus F13y. So we have a value of 4, positive 4 times 10 raised to negative 3 newtons and a negative 4.0 times 10 raised to negative 3 newtons. And we have a 0 value for the y component. So let's add the x and y component. And this will be our final vector for the magnitude and direction of the force. It's F is equal to the square root of the x component and the square of the y component. Since we do not have any value for this, so we only have 6 times 10 raised to negative 3 newtons squared. Squaring it, you can cancel this out, and it will have a value just the same. So how will we imagine that in our figure? So again, we have here F1, 2, and then we have here F1, 3. If we use a parallelogram method, so using parallelogram method, so we can get the vector sum of the forces this way. So I just aligned it at the horizontal. So that's the reason why we do not have any value in the y component, since our vector sum is directed at the horizontal. So we get 6 times 10 raised to negative 3 newtons for the net force. So these two are for you. So you may pause this video and copy the questions on your paper. So you just need one paper to answer these two problems. For number 1, the figure is given already. For number 2, you need to provide it as specified in letter A. These are my references, and that will be it for lecture number 4. Thank you very much. Thank you for watching, and we'll see each other for the next video lesson.